Last time we were working on solids of revolution, which we finished the dishwasher method, and we started working on cross-sectionals in this case, and we described how these cross-sections are not rotations but are, in this case, geometric shapes that pop out of the paper, if you will, to create this 3D image in this case. Well, the last example that we did was one in which semicircles were those cross sections. Let's do one more. So we did one with square, we did one with a circle. Let's do one more. For example, number 10, in which the cross section is triangle. So this is the same region of integration as in the first example in this topic. That's e to the x. I mean rather e to the 2x. And the y-axis, x equals to 4, and well, in this case I didn't write that also the x-axis, it's a limit, but it is. So in this case, well, we want triangles. Equilateral triangles, to be specific, right? Not right triangles, by the way. And this is the picture that we would get if we got these triangles popping out of the paper. Well, so number one, let's set up a formula for a of x, that is the area that we will be multiplying by its thickness. Okay, so that's a of x. And in the previous page, I gave you the different formulas that we use. In this case, well, finding the area of an equilateral triangle, it's not a formula that we use every day and that we memorize, as opposed to length times width over 2, like the right triangle. That's the most common one that we use. So in this case, for equilateral triangles, we got that formula. That's the square root of 3 over 4 top minus the bottom. Alright, quantity squared. Well, in this case, so if we define the top minus bottom from the region of integration, the top function equals, that's root of 3 over 4. That's e to the 2x minus 0, because y equals 0 is the bottom function. That's simply the x-axis again. So top, that's the exponential, bottom, this flat line, this horizontal line, y equals to 0, and that whole quantity squared. Alright, well, so e to the 2x minus 0 is simply e to the 2x, but quantity squared, what is e to the 2x squared? So e to the 4x squared, maybe? Yeah. So power of another power, what do we do with the powers? Multiply. So what is 2x times 2? Just 4x only, right? So careful with the loss of exponents here. So we got the formula to integrate. That's the integral from a to b of a of x with respect x. That's the integral from, well, in this case the limits of integration are pretty straightforward. They're given from 0 to 4, and that's the square root of 3 over 4 e to the 4x with respect x. To get this integration done, well, how about we get the constant outside of the integral to make our lives easier, and just focus on the exponential that we want to integrate. And well, the integral of an exponential is always itself, and well, times whatever constant, the reciprocal of that constant. So that's 1/4 e to the 4x from 0 to 4. This reduces to square root of 3 over 16, and we can evaluate upper limit minus lower limit. That is e to the 4 times 4 minus e to the 0 times, well, actually let me write this as if 4 times 0, and this is simply, no need to reduce to decimals, that's e to the 16. E to the 4 times 0, it's the same as saying e to the 0, but what's any number to the 0 power? 1. Alright, and that's final answer here. Let's do one last problem, but before looking at that problem, well, so notice a pattern here. Let's look at every single region of integration. So, notice how these squares right here form a 90-degree angle with the axis that contains the variable with respect we're doing the integration to, right? For example, we're working on functions of x. We have these squares that are perpendicular to the x-axis. Over here as well, we work with functions of x. These cross-sectionals that were semicircles, did you see how this form like a 90-degree angle with respect to the x-axis? Okay, same thing here. These triangles right here also form a 90-degree angle with the x-axis. That is the variable with respect we integrated to. Now, one note here on the last page of the handout. So, when we have cross sections that are perpendicular to the x-axis, all equations must be solved for what, which is what we did. That means, in other words, functions of x, which is what we did for all these first three examples. However, if the they're telling us that the cross-sectionals are now perpendicular to the y-axis, otherwise the equations must be solved for x, which in other words means need functions of y, which is the example that we're going to do next. Well, so let's sketch the region of integration. That's the square root of x, y equals to 0, that's the x-axis, and the vertical line x equals to 4. And we already looked at this region of integration before. Let's write down the points of intersection because we're going to need this in order to define the limits of integration when we find the volume. So, okay, in this case, if we were to do it with squares being perpendicular to the x-axis, it would look like this. But they're not asking us to create rectangles perpendicular to the x-axis, but rather in the other direction. So let me go back. In this case, well, I'm going to do squares that are rather perpendicular to the y-axis in this case. So what is this going to mean? And when it comes to setting up the integral, we need, and how about we highlight that? This means need functions of y, exactly. So we need functions of y in this case. All right. So this means, okay, y equals the square root of x. To solve for x, square both sides, we get x equals to y squared. All right. And well, this vertical line is already a function of x, if we will. All right. I mean, a function of y, if we will. And well, let's see. So because in this case the cross sections are squares, we will rely on the formula to find the area of a square. So in this case, the area of the square is the length of the side of the square quantity squared. But in this case, we will define, well, in the previous problems in which we defined the region using functions of y, we did the top minus bottom function, right? In this case, because we're defining these functions as functions of y, we're going to do it the other way around. Not top minus bottom, but in this case, what do? Right minus left, right? Rightmost minus leftmost. Oh, let me write it down first. Rightmost minus leftmost. quantity squared. All right, and well, we need to define from the picture which function is the rightmost, which function is the leftmost in this case. So 4 is the rightmost. 4 and the leftmost in terms of y squared. All right, y squared quantity squared. Right, that's the length of the side. Okay, let's go to the integration. Not A, that's volume first. The integral from, not from A to B, but from C to D, of not A of x, in this case, A of y, with respect to y. And well, we have a formula to integrate. Let's just substitute in this integral formula. That's the integral from C to D. Oh, okay, we have a couple of order pairs there, but recall, this is the x, this is x. But in this case, since we're integrating with respect to y, we're going to look at the y values of the points of intersection. So the integral is going to go from 0 to 2. And that's 4 minus y squared, quantity squared with respect to y. And to save time, I will just give you the answer to this integral. If you want to compute it on your own, you should get 256 over 15. Okay? So in this case, well, so all we have to do is square the binomial. You will obtain 3 terms, integrate the 3 terms individually, and then fundamental theorem of calculus. Lucky for us, the lower limit is 0, which will reduce the number of calculations significantly. Question?
Why doesn't the y equals square root of x go into the fourth quadrant?
On the fourth quadrant? Oh, okay, because in this case, so if we had y equals plus or minus the square root of x, right, then we would be graphing both. But in this case, since we're only graphing the positive one, this invisible symbol right here implies positive. Otherwise, it would be negative. And in this case, yes, we would have plotted the one in the fourth quadrant.
So if we get a problem, it will say explicitly plus or minus.
Or minus. So well, yes, maybe plus or minus actually, or maybe they would just give you simply x equals y squared instead of giving you this plus or minus, because that might be confusing if you were given this plus or minus. That'll be weird. So this ends this section actually on volumes using the disc washer and cross-sectional. So what's next? Yes, right here. Alright, so section 6.3. Volumes of solids using cylindrical shells. Alright. Number one, I'm not very happy with the derivation the textbook does. I think it's a little intricate with the symbols and the approach. But I have a different approach to explain this topic. So essentially, what the textbook does is, so you have a cylinder. That cylinder has an outer radius, an inner radius, but also, well, that radius is x units away from the axis of revolution, and the shape of the cylinders are given by the top minus bottom, the usual way that we did in the previous example. However, well, I have a different approach here. Hopefully makes more sense than the textbook's idea. So number one, Number one, we have this region of integration in which we have from A to B, we have f of x, which is the top function, and that's a g of x, which is the bottom function. Alright, same idea as before. Top minus bottom, and then we will discuss the rightmost minus leftmost in a second. So if we rotate this about the y-axis, alright, we're going to get this. All right. And well, so rather than looking at cylinders, how about we think of a lollipop in this case instead, where the axis of revolution is the stick of the lollipop, and the shape of the candy, in this case, which is the region of rotation, will be defined by the functions, by the top minus bottom or right nose minus left nose in its own case. All right. The thing here is, so let me write down the formula to find this volume, so I can show you the connection between the formula and the lollipop approach. So 2 pi integral from a to b, that's some r of x times h of x with respect x. Well, just to be consistent with the units, this r is the radius of the candy, and the radius is the distance from the axis of rotation to the outermost point on the region of rotation. And in this case, I would like to call the number of flavors, because I would like to relate to, have you seen those candies that I think these are spherical candies? If you cut it in half as a cross sectional, and then you look at them from top to bottom, you see layers of flavors. I think they're called rocaletas, right? There's some lollipops from Mexico, but there's also called jawbreakers, right? Here, I haven't seen those in a while, by the way. Well, so you can have those lollipops and with different flavors. How many flavors? X flavors, right? 5 flavors, 7 flavors, 117 flavors, because, well, between the axis of rotation and the outermost point on the region of rotation, how many points are there? How many values of x are there? Infinitely many. So let's just call this x. All right? And that x actually will be in this case, okay, this color. This is the radius. So the radius of the candy will be given by the number of the flavors on the lollipop, right? So number of flavors. Number of flavors. But what about h of x? H of x defines the shape of the candy, and that's always the shape of the candy, and that's always the top minus bottom thing in this case. Well, initially it might be weird. The part that might be weird for a while will be the R, because, well, R is a number of flavors, which is x, minus the position of the axis of rotation. But number one, what is this axis of rotation? X equals to 0, right? And it will make more sense when we do these rotations about other axes of rotation that are not the x-axis or the y-axis. In the meantime, well, let's do some of those. Oh, let me discuss the vertical. I mean the other way around. And yes, so instead, this time I'm gonna have this region where this is some f of y, and this is g of y, and, well, the axis of rotation in this case is the x-axis. Now, one main difference here. So the volume in terms of y, 2 pi integral from c to d. This is from, well, I should have done it the other way around, c to d. That's in this case r of y, h of y, with respect y. Okay? So in this case, well, just think of a sideways lollipop in this case. And the number of flavors, it's going to be, well, which direction am I sliding this? Is it the x direction or the y direction? It's in the y direction, right? So that's going to be the number of flavors, again. of the lollipop. And again, h of y will be the shape of the candy. Right, the shape of the candy. Well, in this case, but this is not going to be top minus bottom, but in this case, this will be right minus left. Right minus left. And let me go back to top minus bottom. Alright, what's the main difference here between the disc washer method and this new method called the shell method? So in the disc method, okay, let me zoom everything out so you can see the whole thing. Alright. In the disc and washer method, when we rotated about the x-axis or about other or horizontal line that was not the x-axis, we use functions of x, that is rotation about the x-axis, functions of x. When we rotated about the y-axis, that was rotation about the y-axis, functions of y. In this case, it's the reverse. Notice, you might have noticed the difference when I was doing the picture here to relate the formula with the picture here. Notice I'm using functions of x, but we are rotating about the y-axis instead, right? This gets reversed when we go about the shell method. And in this case, functions of y, we use them when we rotate about the x-axis. So how about we look at some examples? So let's see. Let's find the volume of a solid obtained when rotating the region y equals to x to the square root of x, the x-axis, and x equals to 4. Notice all the information is pretty much given in terms of x. That means we would expect most likely to rotate about the axis of the other variable, in this case the y-axis. Okay, and so as a note, functions of x. Alright, not functions of y as we did in the disc washer method. Alright, so let's draw the graph. So we have the square root of x. What else? The x-axis and x equals to 4. Now, they're telling us that the rotation is going to go about the y-axis, and that is, we're going to do this right here. We're going to do that. So, this axis of rotation, think of it as a mirror, and that should give us the following picture. Oops. I don't know what happened here. Okay. Alright. Now that's too big. Alright. Like this. Sort of, let's make it look like, let's give it some character of rotation. So it looks like this, right? Well, so let's think of a lollipop actually having this weird shape. It's not one of those typical lollipops that have a spherical candy tied to it, or a cubic, or like a rectangular box shaped type of candy, like those in the Sis candy that you may have seen those before. Well, so this is something weird, but let's describe the volume of this solid of revolution. Number one, this rectangle right here is to describe the shape of the candy, that is top minus bottom. That's volume 2 pi integral from a to b r of x over, times h of x with respect x. Okay, so let's see. h of x is the height of the shape, or is given by the height of the shape, the difference between the two functions. In this case, the top is the radical function and the bottom is the horizontal line, y equals to 0. But now the r of x is the radius of the candy, or the radius of the solid, right? And that's, again, coming back to the candy example, it's how many flavors do we have in this case? In this case, just X number of flavors, right? And well, I'm going to write something else to make more sense out of it. And if it doesn't make sense for now, it will make more sense when we do this shifted this shifted versions of this axis of rotation. So in this case, for the radius, okay, to describe the radius, it's going to be x minus the position of the axis of rotation. So what's the position of the axis of rotation? Zero. So if we were rotating this about the axis x equals to -3, for example, this would have been x minus -3, for example, which would become x plus 3. And well, yes, this would have been weird because this is like having a weird lollipop in which the candy is not stick to the actual stick. It will be floating. That's kind of weird to think about, right? But who knows? I mean, there's technology advancing every day, and maybe they come up with new floating sugars, or you know, this nanotechnology doing this and all that, you know. So anyway, so that'll be the radius, and that's top minus bottom, that's square root of x minus 0. And the limits of integration are the same. So I'm using the same region of integration. That's the origin, 0, 0, and 4, 2. So the limits of integration for this region go from 0 to 4. And let's just simplify this real quick. So x minus 0 is simply x. Root of x minus 0 is simply root of x. I'm going to get 2 pi x root of x with respect x. Well, in this case, we cannot integrate a product of two functions. There's no such thing as a product rule for integration, like we had a product rule for differentiation. However, we will look at differentiation, at integration by parts soon, which is kind of a product rule, but it's not exactly a product rule. So I'm going to rewrite this as 2 pi integral from 0 to 4, and that's x times x to the 1/2 with respect x. Combine everything into a single factor, into a single term. Well, we have an invisible one, which is we need to add the exponent. That's going to give us 3/2, right? 2 pi integral from 0 to 4 x to the 3/2 and 2 pi the integral of x to the 3/2, that's adding 1 to the exponent. That's going to give us 5/2 over 5/2 evaluated from 0 to 4. Okay, so careful with the division by a fraction. What do we do when we divide by a fraction? Multiply by the reciprocal. So 2 times 2/5, that's going to give us 4/5. 4 pi over 5 x to the 5/2. Well, actually, let me just, yeah, that's fine. Evaluate from 0 to 4. Okay, so that's the same as saying 4 pi over 5. And that's a 4 to the 5/2 minus 0 to the 5/2, which is going to be 0. Well, I'm worried about this quantity here, that 4 to the 5/2. Because, okay, you may see something like this on an exam, and it might be tricky without a calculator. So recall from properties of radicals, let me use a different color to show you this calculation. I'm going to do this calculation below. Okay, so this 4 to the 5/2, I'm going to write it in form of a radical. So recall that the denominator of the rational exponent is the index of the radical, isn't it? In this case, it's going to give us a square root. All right, so this is the square root of 4 to the 5th power. However, This form may not be the most convenient in a situation in which we don't have a calculator, which, for example, right now I don't have a calculator. Well, recall there's another way to rewrite this radical. The other way is the square root of 4 and have the 5 outside of the radical, right? Why is this last form more convenient? Because, well, what is 4 to the 5th power? Really big number, isn't it? Can you find the square root of that big number on the top of your head? No, so it's easier instead to take the square root of 4, which is 2 to the 5th power, and what's that number? 32. Alright? So it's important to consider these properties of radicals when running into this situation, which we will use this later in other problems. So this will be, coming back to the integral, 4 pi over 5 times 32 minus 0. And well, 32 minus 0 is just 32 times 4, that's 128 pi over 5. Okay? This problem in particular, I wanted to do the whole thing and not just give you the answer precisely because this radical situation. Question?
I'm a little bit confused on how you got x for r of x. Could you go over that again, please?
Yes. So, the radius of the solid given by r, that's extending in the horizontal direction x minus, in this case, the position of the axis of rotation, which in this case is 0. If we had, for example, let me do this in a different setting. If we had, instead of rotating this around about the y-axis, but rather about x equals -5, for example. All right, not x equals to 0 in this case, which is the y-axis. Well, this would be reflected this way. All right, and in this case, the radius, it's going to be, again, that radius gets extended in the horizontal direction by x units. In this case, minus the position where we have the axis of rotation, which is -5. So this term would have been, in this case, x plus 5 instead of x minus 0. All right?
Why isn't the radius just 4?
No, because the radius is the distance from the axis of rotation to the outermost point in the solid that we rotate. The x equals 4, that's going to define the shape of the solid, which, depending on the direction that we do the problem, if it's top minus bottom or rightmost minus leftmost. But I see what you're saying. Yes, the outermost point is when x equals to 4. That is true. But in this case, here we would be saying that we would have, like, coming back to the candy example, we would only having 4 flavors, right? But how many flavors can we have in the candy? X flavors, right? Even more than 4, 17, 25, many more flavors. So I guess I understand when I first took this class, I had a hard time understanding the radius too, but I think it's going to make more sense when we do the rotations about other axes, and when we do more problems. So let's see. So for the next example, let's see, we have find the volume of a solid obtained when rotating the region bounded by y equals x minus x cubed, y equals 0, x equals 0, x equals 1. Well, they're giving us a lot of information here, which is good because, number one, again, we are going to rotate this region about the y-axis. So which functions are we going to use here? Functions of x or functions of y? functions of x, right? Recall that in this case it's the opposite in the shell method as opposed to the disk and washer. Disk and washer, they're the same variable. In this case, functions of x. Okay, so let's do the graph. Well, number one, the graph of y equals to x minus x cubed, which I will just give you the graph. This one looks like this. All right. This one you can verify this using a graphing calculator or etc. On the exam, you will be given for a function that it's easy to graph, not because I mean you're not expected to know how to graph this from the top of your head. All right. So that's why in this case, just for the example, I'll give it to you, but I'm not going to draw the entire graph in this case because notice the limits of the other limits of integration. So y equals to 0, that's the horizontal, that's the x-axis. What else? X equals to 0. All right, x equals to 0, and in this case we only need this portion of the graph where x is also equals to 1. And we will rotate this about the y-axis. This should mirror this. All right. And well, let's try and give it some effect of a solid. It's kind of hard to make it look 3D, but essentially it's being rotated about the y-axis. We're getting this solid here. All right. Well, so again, this solid has a radius. All right. So now coming back to the question before, why is in the previous example we as an outermost point was x equals to 4, but in this case the outermost point, well, it's different points depending on how high we are in the shape of the graph. So we're gonna do the top minus bottom. Again, let's write down the formula. V equals to 2 pi integral from a to b r of x h of x with respect to x, where the r of x, again, what's the radius in this case of this shape?
X minus 0?
Just x, or x minus 0. That's r of x. Because 0 is the position of the axis of rotation, and from here, that's okay, x minus 0. I mean, after some practice, after you do a few of this, you won't have to write this minus 0. Just the x is fine. And the reason I'm writing this minus 0 is so you can see how we are setting up the region of integration. So, and then what about the top minus bottom? Which one's the top? Isn't it the curve?
Yeah.
So, which is defined by x minus x cubed minus the bottom, which is also 0. With respect to x. And the limits of integration, well, they're given from x equals to 0 and x equals to 1. And well, so this will give rise to the following integral. So 2 pi from 0 to 1 x times x minus x cubed with respect to x. And well, let's distribute the x over these two terms right here. 0 to 1, x squared minus x squared, minus x to the 4th. And well, let's just integrate term by term. But just to save time again, I will give you the answer to this integral. That's going to be 4 pi over 15. Okay?